The compact X-ray free electron laser, or CXFEL, is being developed by ASU researchers with the goal of surpassing conventional X-rays by examining atomic and molecular scale structures with newfound clarity. Joining us now is the director of ASU's CXFEL Labs. There he is, Arvinder Sandhu. Arvinder, good to have you here. Thanks for joining us.
Thank you so much for having me.
So I'm reading a lot of stuff here. I don't know what I'm talking about here. What are we talking about? It sounds like it is the next generation of X-ray, true?
That's correct. So CXFEL is a unique machine which is first of its kind in the world. And what we are doing is we are combining very high power laser technology with miniature accelerators to produce X-rays that can help us see at the atomic scale. And this means that we can now understand the working of proteins. We can do medical imaging in a safer way. We can also look at the materials which are important for light harvesting and energy generation. And just to put this in perspective, what's special about CXFEL is that there are only 5 or so X-ray lasers in the world. And they're all very big machines. They have accelerators in tunnels which are kilometers long, and they cost billions to build. Whereas CXFEL is a 30 feet long machine. It fits in a lab, and it costs only millions, so it's accessible to everyone.
I was going to say, when researching this, it sounded like it was a mini particle accelerator. Is that
Indeed.
what it is?
You're right. One key part of it is a mini accelerator. The other key part is lasers. So we bring them together in a very unique way to produce X-ray radiation by wiggling the electrons.
And it's basically, the idea is you can learn what proteins are and what they're doing.
That's right. So using X-rays, we can, I can give you an analogy here, which might be useful. If you're, let's say, sitting by a lake shore and you're relaxed and watching the waves come by, the waves may come in predictable patterns, but if there are any rocks near the lake shore, the waves will deflect off the rocks and will make very interesting patterns. And what we do is the same thing. X-rays for us are the waves which hit the atoms inside the protein, which are like rocks in the lake. So the X-rays deflect.
Oh, wow.
And we capture these deflected X-rays on a detector, and from that we back calculate where the atoms were in a protein, and therefore we can understand what the structure of the protein was.
Now, is quantum physics involved with this at all?
Of course, it is quantum physics, because not only we want to understand where the atoms are, but we also want to understand how the atoms move. And the atoms and the electrons inside atoms move at really fast quantum timescales, which approach millionth of a billionth of a second. So we want to make this machine to capture not just static pictures, we want to make the movies of these molecules as they're in process of undergoing chemical reactions or transformations.
And you've got a success here of late regarding proteins, correct?
That's correct. I'm very happy to report that, thanks to excellent work from our team of scientists and engineers, we have solved the very first protein structure at ASU. And what it means is that now we can invite other researchers worldwide to join us in this effort, and we can accelerate the pace of scientific and applied discovery in these fields.
And when you talk about accelerating that pace of discovery for what? How disease works, how medicine works, both of those things?
A lot of things. So this is a very high impact machine. In fact, it has a generational impact on health, medicine, science, and technology. I'll give you an example. If you understand the protein structure, then you can design drugs that bind to that specific structure. So it helps in devising new drugs for treatments of diseases like Alzheimer's. You can also do medical imaging in much more safer way with much less dosage of the X-rays. So, and of course, once you have these ultra-fast X-ray pulses, you can understand how the quantum particles work inside materials, and you can come up with ways to make quantum devices which can harness energy, which can transfer energy, and we can also find ways to store energy in a much better way.
I was going to say, I keep thinking medical and I keep thinking health because you're looking at proteins here, but there are all sorts of applications here, aren't there?
Definitely. It touches on a lot of fields. In fact, you can also apply it in computer chips. If you want to image those computer chips which have features that are so small that you can't see them under a microscope, you can use these X-rays to see those computer chips, which are modern computer chips.
Yeah, and this thing is so small, you can keep it in the basement of the Biodesign Institute, right?
It is super accessible. We hope, with our success, we hope that we can make it so accessible that you can have them not just in university labs, You can have them in hospitals. You can have them in industry. So everyone can have access to this technology, which is currently limited to just few facilities in the world.
Last question, and we're running out of time here, but I want to know, is there a next step? Is there a second version of this?
Right. So we have achieved our first milestone. We have produced the X-rays. Now we want to make them into a laser-like beam of X-rays, which will open up even more applications for us. And that's what we want to achieve with the help of our collaborators, with the help of ASU, with the help of community support. We want to get there to basically support our young scientists, to place the critical instrumentation in place to achieve this goal.
Oh, wow. Arvinder Sandhu, again, ASU, CXLS, we're going to let the letters play for themselves. Congratulations on this, and thanks for sharing the story. It's fascinating.
Thank you very much for having me. I'm happy to come back here again to report on
All right.
success.
Well, we may just ask you back there. Thank you, sir.
Thank you so much.